In this section, we're going to talk about our introduction to probability, which starts to lay the groundwork for what we're going to do in Chapter 9 and Chapter 10. Let's talk a little bit about probability for a moment. Probability theory has been around for a couple hundred years. It's one of those branches of mathematics that some students just find totally confusing. And that's understandable because probability was first developed by a bunch of mathematicians who were degenerate drunks and gamblers. It's just what it is. The reason they started dealing with probability is because they wanted to understand their odds and how much they could win and or lose. That's where it comes from. Which is why a lot of the problems that we will do will involve roulette, it will involve cards, it will involve games of chance, because that's what they are, okay? And this stuff flows through, though, to everything that happens in the world, okay? If you guys have ever seen the original Jurassic Park, Jeff Goldblum plays the mathematician, and he talks about chaos theory. Chaos theory starts from this, okay? This is where it gets its basic start. All right, so when we talk about probability, we're going to introduce some terms that are important, and you need to know what they mean. Because if you don't know what they mean, it's going to be extremely difficult to actually follow through what I'm doing. All right, we're going to talk about random experiment. This has outcomes that we cannot predict. For example, flipping a coin. Can I accurately predict how that coin is going to land every single time that I flip the coin? No, I can't. Okay? Then we're going to talk about trial. The trial is the repetition or actual activity from your random experiment. So, random experiment, flipping coins. The trial, I'm actually flipping a coin and seeing what it's doing. Does it land head? Does it land tail? And I can repeat this a number of times if I need to. Now, when I say that I can repeat this a number of times, that's because I'm interested in the outcomes. Possible result from each trial. Oops, sorry. Possible outcomes from each trial. I want to record every single thing that I do. Then we're going to talk about sample space. That's going to be all the possible outcomes for a particular random experiment. Now, when we talk about this, there are two different ways to look at the sample space. The theoretical and the experimental. Theoretical means I list the possibilities. For example, let's say that I have two coins. My trial is flipping both coins and then recording what I get. What is the possible sample space? Well, there's only four possibilities. I'm either going to get a head-head, tail-head, head-tail, or tail-tail. And yes, head-tail and tail-head are two different outcomes. Why? Because I'm talking about two different coins. Either the first coin comes up tail and the second coin comes up heads, or the first coin comes up heads and the second coin comes up tails. Those are two different outcomes. So let's talk about this random experiment. What are my outcomes? Well, as I just said, you can either, and we're going to talk about one coin here, flipping a fair coin. And let's discuss that word for a moment. What do I mean by fair? Somebody tell me what I mean by fair.
Even chance for all outcomes.
I got even odds, even chances for getting the same outcome. Okay? Fair. That means that both possibilities in this case are equally likely. Okay? or I should say the results are equally likely. Okay? So all results so consider the lowly nickel. Is that a fair coin? You got equally likely chances of getting heads or tails, right? What about a quarter? No, unfortunately, that's not a fair coin. Who's got a quarter? Surely somebody in here has got a quarter. A simple quarter. I'll give it back, don't worry. Okay. If you've got a quarter, look at the edge. What do you notice about the edge of that quarter?
It's got like little streaks of lines.
Yeah. There's actually two different metals in here. Okay? And that copper alloy is heavier than the other alloy, which means it's not a fair coin because more than likely the heavier side will always land down. So quarter's not necessarily a fair coin. Thank you. So when we say fair, and we're going to define this in a number of different things that we're going to talk about, let's talk about what our outcomes are. Remember, one coin. Outcomes are heads or tails. Are there any other possibilities? Well, unless you're flipping it over some sand, it's going to land on one side or the other. It's never going to stand straight up. Okay? And the only time it's going to stand straight up is if it's in some sort of substance that it can. So it's heads or tails. But what's our sample space? Well, the sample space, we're going to label that S, and that's going to be the set of the possible outcomes. Notice that I've separated them by a comma. And if I had more than two, for example, a fair die, and let's further refine that, a fair six-sided die, I would have six possibilities, 1, 2, 3, 4, 5, 6, for my sample space. Now, what is the actual trial here? Well, the actual trial is flipping the coin. Any questions? All right, let's look at this problem right here. We're going to use this spinner. We're going to assume each outcome is equally likely, and we want to determine the sample space. But let's actually look at that spinner. Everybody in here, hopefully, maybe, has played a game that has some sort of a spinner in it. Whether you're playing Twister or anything that requires a spinner, you know what the spinners look like. Are those things fair? Are the outcomes on any given spinner that comes with a cheap board game equally likely? No, they're not. Number one, that grommet in the middle is not always put in there perfectly. That arrow is not going to spin smoothly every single time. So we want to talk about the fact that this is going to be equally likely. So what is my sample space for this thing? Well, since I'm assuming that everything is equally likely, I'm going to list each one of the possibilities. And that's it. That's all there is to it. That's how you list your sample space. And that's assuming that we're talking about a simple activity. They get more complicated. For example, let's draw a tree diagram for the random experiment of flipping a coin 2 times and determine the sample space. Now this one's not that hard to list without the tree diagram. The reason we talk about the tree diagram is because these things get complex, and we want to make sure that we are following and listing every possibility. So if we're going to flip two coins, or we're going to flip a coin twice, which by the way would be the same thing as flipping two coins. So I flip one coin, I get a head, I flip the coin again, I get a tail. That is an outcome. So we start with a tree diagram. And it's always going to be binary, meaning there are two possibilities. So we flip the coin. Or actually, let's just call it the first flip. Well, the first flip, what are my possibilities? I'm either going to flip a head or I'm going to flip a tail. Then I'm going to do the second flip. Once again, as I flip the coin, I only have two possibilities, head or tail. But I need to do this for both of the first possibilities in the first flip. And now I'm going to follow the branches of the tree diagram to list my possible outcomes. I start here, and this is a head, and then that takes me to a head. So I have head, head. Then I'm going to follow this one and then this one and get head, tail. This one will be tail, head. And then this one will be tail, tail. And I have listed the four possible outcomes. And the sample space S will be listed as a set, HH, comma, HT, comma, TH, comma, TT. Notice that I do not put commas between these values because I want you to get in the habit of separating the outcomes by commas, but the outcomes themselves, if there's more than one possibility in there, will be one single string without separation. Because if I did something like this, that would make no sense because I can't get just one head. I have to have two outcomes for that particular trial. Does that make sense? Now, notice something here. I took a coin and I flipped it twice. How many possible outcomes did I get? What if I take that coin and flip it 3 times? How many possible outcomes will I get? What? 8. Same thing as what we were doing in the last sections with the Venn diagrams, right? If I have distinct regions, the number of sets, or I should say, let me try that again. If I have a certain number of sets, the number of distinct regions is going to be 2 raised to the n power, where n is the number of sets. Same thing happens here. I have 2 outcomes in each trial because I'm flipping the coin twice. That means I will take 2, raise it to the second power, and get 4. If I have 3 coins, or I'm flipping a coin 3 times, that means I will have a total of 8 outcomes, 2 to the 3rd power. And let's explore that by looking at this problem right here. An experiment consists of studying the number of boys and girls in families with exactly 3 children. Let B represent boy and G represent girl. What is the sample space? That's what I want to know. How do I figure that out? Well, I've got to list all the possibilities, right? Well, let's think about this. There are 3 children. Now, no matter what, the children will be born in chronological order. And I know I've got a set of twins. My wife gave birth to a set of twins. Let's put it that way. I don't actually own them. Okay? My wife gave birth to a set of twins. my son Ian is 2 minutes older than his sister Megan. So that is in chronological sequence. They are not going to be born at exactly the same time. Okay? So, I have 3 children. That means the first child can either be a boy or a girl. Now, I'm not going to get into philosophic debates about what's currently going on in the media, about gender identity and everything. We're just using boy and girl as an example, okay? The second child, and I'm going to move this down a little. Then we're going to talk about the second child. The second child, once again, is either going to be a boy or a girl. And then we're going to talk about the third child. Once again, the third child in this scenario will either be a boy or a girl. And each one of the preceding genders will lead off to 2 possibilities. And then I will follow the branches to establish my sample space. This will be boy, 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 girl. This will be boy, girl, boy, boy, girl, 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 boy, boy, girl, boy, girl, 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 boy, and then finally girl, girl, girl. I have 8 possibilities. So a family that has 3 children will have one of these possible combinations. So let's list the sample space. And you don't have to try to list the sample space in alphabetical order or anything like that. You're just going to list the space so that you have all possibilities. And it is a set, and you need to go ahead and make sure that you write it in set notation. Notice once again, I am separating each outcome by parentheses, but each outcome does not have any separation between the letters. I forgot where I was. And hopefully I didn't miss any. Did I miss any? Because I was too busy talking. 3, 6, 8. There we go. That's the sample space. Any questions? Seems pretty easy, right? Now, let's define this right here. An event. The event is an outcome or a set of outcomes of a random experiment. What we mean by that is we have a sample space, but sometimes we're only going to consider certain outcomes. And that's what we're going to call our event. And an example of that is going to be checkpoint 2 from the textbook. Let me scroll down to this. And we're going to talk about this one. Okay, first off, let's look at this right here. The thing says, suppose a die is tossed. Write the given events in set notation. Die is singular, dice is plural. Okay? Just to make sure. Another thing that I want to talk about is the fact that this has not been defined. It just says a die is tossed. What kind of die is that? I have no idea. Because if you know anybody who plays Dungeons and Dragons or any other kind of role-playing game, you know the die come in all kinds of flavors. So for the purposes of this particular example, we're going to assume a fair six-sided die. And die come, like I said, you can have a four-sided die, a five-sided die, a 22-sided die. Okay? We're going to assume fair six-sided die. Now, write the given events in set notation. So this first one, part A, says the number showing is less than 3. Well, first off, I need to know what the sample space is in order to be able to answer these questions. So let's list the sample space. And since it is a fair six-sided die, there are only 6 possibilities. A 1, a 2, a 3, a 4, a 5, or a 6. Now, part A, the number showing is less than 3. Well, there's only 2 possibilities here, right? 1 and 2. So that means my event, A, and we'll call it A, is simply equal to 1, 2. I've taken the 2 outcomes for that event, A, and I've listed them. And it's simply a set. Notice that we label sets with what? Capital letters. So, we'll go to the next one. Event B. The number showing is 5. That's pretty simple, right? There's only one possibility for that. And it looks just like that. Now let's consider C. The number showing is 8. Yeah, that one doesn't work, does it? So what would C look like? It's the empty set. I'm either going to establish it as this with nothing in it, or I can use the empty set notation that looks like that. Okay? As a continuation of that, let's look at this one. It says, which of the events listed in checkpoint 2 is certain, and which of the events are impossible? Which of the events in checkpoint 2 are certain? None of them are certain. Why?
It's random.
Exactly, it's random. I have no idea what's going to come up. I take that six-sided die and I roll it. Am I guaranteed to get a 1 or a 2? No. I roll it. Am I guaranteed to get a 5? No. It's a trick question to make sure that you understand exactly what's going on. And if you answered A or B, don't worry about it. You weren't alone. A lot of people do that. Nothing is guaranteed. Okay? Nothing. But what about impossible? That would be event C. So none of them are certain, and event C is impossible, assuming that it is a fair six-sided die. Obviously, if it's an 8-sided die, it'll happen. Okay? Which is why I'm so keen on telling you the parameters of what we're doing. Okay, let's talk about set operations for events. And this is kind of similar to what we've been doing. We're going to let E and F be events for a sample space S. That means they have to occur in that sample space, okay? It's part of a single sample space. E intersect F occurs when both E and F occur. E union F occurs when E or F or both occur. You guys already know this, right? We have already established this fact previously. And E prime or E complement occurs when E does not occur. This is just simply taking what we've learned about sets and applying them to these probabilistic events. Okay? Now, let's look at checkpoint number 4. Does everybody have all that? All right, we want to write the set notation for the given events for the experiment of rolling a fair, remember, 6-sided die, if E is equal to 1, 3 and F is equal to 2, 3, 4, 5. Once again, before I start this thing, I need to establish what my sample space is. But we already know what it is. And it's one of those that is ubiquitous. We will use it a lot. So there's my sample space. Now, I want to write the set notation for given events. Let's look at set A. Set A is going to be the intersection of E and F. And if I look at this, I note that E has 1 and 3 and F has 2, 3, 4, and 5. And the intersection is going to be 3. That's it. What overlaps here? And you must write it in set notation. Now, you can go ahead and quickly establish a Venn diagram if you so desire. Okay? And I'll write the event E. That's kind of small, isn't it? Can you guys all see that? That's better, right? I'll write the event E right here. And I know that E will have 1 and 3 in it. And then I'm going to write the event F. I'm going to assume there's some overlap. And I know there's overlap because I just showed you that there was overlap. And I can write 3 right here in the intersection of E and F. E still contains the value 1, and F is going to contain 2, 4, and 5. I'm missing one, aren't I? I've got 1, 2, 3, 4, 5. What am I missing? And where would the 6 go? In the universal set out here. Okay? So let's talk about E union F. That's going to be everything that's in E, or everything that's in F, or everything that's both in E and F. Which means I'm simply going to write set B as 1, 2, 3, 4, and 5. It contains everything except for what's outside of those 2 sets. And then finally, E complement. What is E complement going to be? Remember, E complement is going to be everything that's not in E. So that means I'm looking at this value, this value, this value, and that value. They are not in the set E. So let's write E complement, which could also be written as set C. That's 2, 4, 5, and 6. We've already defined what disjoint sets are. Well, guess what? We can simply change sets to events and get this. Disjoint events are events E and F, and they're disjoint if E intersect F is the empty set. Notice that everything that we've done in set theory follows nicely into probability theory. There's an intersection there. There's an overlap. So given that definition, let's look at checkpoint number 5. In example 5, let F be equal to the set 2, 4, 6, and K be equal to the set 1, 3, 5. Basically, we're talking about a fair 6-sided die. Okay? So what's the sample space? And notice that I write the sample space every time I do the problem. It does not matter that I've done a number of rolling die problems, okay? I'm still writing the sample space out. Why? Because that way I've got it in front of me, and hopefully I'm not going to make any mistakes by forgetting something. It's really easy to forget something. For example, let's say that you have the following experiment. You're going to flip a coin 4 times, and you want to record the sample space. How many events are going to be in your sample space? 16. How easy would it be to forget to write one down? Because you're talking head, 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 tail, and then you got to go through all of them. It would be extremely easy. Let's say that you had 8 trials in there. How many events would be in your sample space? Say what? Are you sure? Okay, well, we had 4, that was 16, which means that 5 would be 32, which means 6 would be 64, 7 would be 128, and 8 would be 256. It would be extremely easy to not list one correctly or make a mistake when you're actually doing a problem such as this. I always list the sample space because that way it helps minimize the potential for error. All right. This one says G remains the same, which means that set G is equal to the following. So write that down. Are the given events disjoint? Is the event F, or I should say, are the events F and K disjoint? In other words, is there any overlap between F and K? No. So yes, they are disjoint. And the reason for that is because F intersect K is equal to the empty set. Therefore, F and K are disjoint events. Oops. There we go. I hope if I could spell disjoint, huh? What about F and G? Well, what's the intersection between F and G? Does it exist? Yes, it does. Because for F and G, F has a 2 and G also has a 2. Therefore, F intersect G is equal to the event. Therefore, F and G are not disjoint events. Okay, now we're going to talk about the basic probability principle. Yes, I'm sorry.
How did you know G was 1
Because that's in example 5, and I was just pulling it in
Okay.
instead of going into the book. So we're just... does that make sense now? I'm sorry, I should have been more clear about that. Okay, let's talk about basic probability principle, and that's this right here. There's a lot here. Make sure you get it all. We're going to let S be a sample space of equally likely outcomes. We're going to let event E be a subset of S. Then the probability that event E occurs is given by the following formula. P of E, notice this is a capital P. It means probability of the event E occurring will be equal to the number of possibilities in the event, E, divided by the number of possibilities in the sample space. It's simply a ratio. This one is the number of elements in event E, and this is the number of elements in the sample space. Let's look at an example that goes with this. And I'm going to go back to the fair six-sided die. The sample space for a fair six-sided die is equal to this. I want to find, the probability of rolling a 6. Well, I need to know what the event is. I need to know what the sample space is. I have the sample space. What is the event E? E is simply this set. And it contains the single element 6. The probability of 6 is going to be n of E over n of S. Which is going to be simply 1 over 6. Because there's one event in E, and there's 6 events in S. So the probability of taking a fair single-sided die and rolling a 6 on any given roll is 1 in 6. This is what we call theoretical probability. Because if I actually took the die and I rolled it, I only have a 1 in 6 chance of actually getting a 6. It's more likely that I will get a 1, 2, 3, 4, or 5 instead of the 6. Because what's the probability of not rolling a 6? Yeah, the probability of not a 6 is simply going to be equal to 5 over 6. Because these values are not in my event. It's more likely that I will roll something other than a 6. Any questions? Okay. We'll stop there. We'll pick this up on Thursday. We will finish this chapter or this unit on Thursday. You guys have a good day.